If you would recall, yesterday, I posed the following problem, maybe the following two problems. I wanted to find the distance between the points 0, 0 and 3, 9, but following two different paths. First path is just a straight line, so I want the shortest distance from 0, 0 to 3, 9. But then I want the length of the path going from 0, 0 to 3, 9 along the parabola. I want to know how long the road is if it's a parabola from 0, 0 to 3, 9. And then we specified this specific parabola, y equals x squared. We could worry about whether there are other parabolas, parabolic paths between 0, 0 and 3, 9, and whether they would give you the same distance. But let's specifically use this one. So the path y equals x squared. So first things first, this is not an appropriate problem for Calc 1. This is not a problem that we should throw at Calc 1 students. This problem next semester will become just trivial. There's a formula for it, and you'll just know the formula. Some of you may have already looked the formula up and finished the problem, which is fine. This is not an appropriate problem for Calc 1. We don't have the complete tool set that we would need to solve this problem. That's what makes this problem a great final exam problem. It would be unfair to drop this onto a final exam problem, but the reason that it would make it, that's what makes it a great final exam problem, is that it involves calculus thinking. Now, this is not a final exam problem where I would expect to find an exact answer. If you give me an exact answer, you've clearly been through Calc 2. Why am I bothering to grade your final? Right? It's like, well, why are you taking a Calc 1 final if you've obviously been through Calc 2 because you dropped the exact value onto this problem? That is, of course, if you have the supporting work, because Wolfram Alpha will give you the exact value of this problem, but only if you know how to ask the question. So there's that as well. That makes sense? This is one of the things we have to worry about in math class. In math class, sometimes I like, oh, are there any questions? And there's 3 levels of that question, 3 levels of response to that question. Lowest level, least pressure, no, because we got everything. So I'm like, oh, are there any questions? And you're like, oh, no, everything has been perfectly clear. That's the first level of the response to, are there any questions? Second level response to, are there any questions, is, yeah, what are you talking about? In which case, that's just my prompt to say, let me talk about it again from a different angle or in a slightly different way to try to answer your question. Or, how do you do problem number 5? And I'm like, oh, I don't know. Wait, I'm supposed to know that. And then I do problem 5. Then I do problem 5. Then the highest level of response to that question is no, because we don't even know what to ask. Are you still speaking the language that you started speaking at the start of this class? I thought we had agreed at the beginning that this class would be in English, and you are now speaking gibberish. What the heck, man? So those are the 3 levels of response to, are there any questions? No, yes, and no. So one of the reasons that I think this is a great problem, even though you don't have the tools, and one of the problems that I have with the way that we teach math is that we say, here's the thing, here's the tool, off you go. But I have a more important question, not can you solve the problem? Because at this point in your mathematical career, I do not care if you can solve the problem or not. That's irrelevant to me right now. Asking this question at this point in your mathematical career, here in Calc 1, near the end of Calc 1, but here in Calc 1, has a different purpose than finding out if you paid attention to how to do problems. It's way different than if I ask a question, what's the derivative of this function? And that'd be me trying to find out Can you follow the chain rule, the product rule, quotient rule, all that other stuff? Can you decide what rule to use and apply it properly? Here, I'm asking a different question. Do you understand the thinking behind calculus? At the very beginning of this class, I said what calculus is about. There's the two big questions. That's secondary to what calculus is about. That's how we go about getting at the core subject of calculus. In all of your math classes, there's kind of a leap forward. There's a new thing. That's why we give the class a new name. You start off in arithmetic. You just got to learn how these numbers work. After you do arithmetic, you do some algebra. And it's like, oh, hey, remember those numbers? What if instead of base 10, it was base x? And you start learning more about arithmetic through algebra. Then you start to visualize things. Then we give you a new class called geometry. And it's like all shapes and measuring the shapes. And then usually we go back to do some more algebra because algebra is always on. And then you do some trigonometry. It's like, well, hey, remember those shapes? Now we're going to analyze them a little bit more. More measurements, more stuff about the shapes, more things we can do to measure those shapes. Then we get into pre-calculus. And you're like, oh, ooh, now it's happening. Pre-calculus. That's just another algebra class. It's like, well, hey, remember algebra? And remember, yeah, and you're like, oh, yeah. And remember all those geometric shapes that we talked about? And you're like, oh, yeah. Let's combine those two and do some more algebra and start talking about functions. It's just another evolution in your algebraic understanding. And then you get to calculus. And the question comes up, what's calculus about? And for a long time, I struggled with what the core answer to that question is, because usually people talk about it's the mathematics of change, right? People, oh, it's the mathematics of change. And yeah, but what's the big thing that shows up besides change in calculus that makes it different from your previous classes? And then we talk about the two big questions. What are the two big questions? Tangent to a curve and area under a curve. Those are the two big questions. That's not really what calculus is about. That's not really the story of calculus. That's how we go about it. What is calculus? It's infinity. That's the international symbol for infinity. Or bandits are about, I don't know. Or I have fake binoculars. But yeah, the infinity. Calculus is it's the rigorous study of infinity, because this is a weird concept. This is a weird concept. And we don't understand it very well at all. When we're first starting in calculus. By the time we get to the end of calculus, we're like, oh, we are well versed in infinity, insofar as it's very weird. And so calculus is where we start to rigorously study what happens when we go from just from 0 to infinity. When we go from a discrete set where we can just start counting things to a continuous set. And that brings us back to this problem. This problem is just calculating an arc length. Spoiler alert for those of you who want to look this up. It's just arc length. We call this style of problem an arc length problem. And it leads to an integral. And y'all are like, oh, but it leads to an integral that we can do, right? I'm like, oh, no, y'all can barely do integrals. The integral that this one leads to is trigonometric substitution, which is my favorite kind of integration technique. But we don't have that yet. But we do, well, we have attempted to give you the idea about integration. Integration is multiplication, but one of the factors is continuously variable. The big deal with integration is that we're trying to find a sum, but not a discrete sum, a continuous sum. There's nowhere to put the plus signs. That's the interesting thing about calculus. That's why those two big questions for studying it are so useful to us here in calculus. Not because later on, when you're working at Twitter, because you like super long hours for no money and you like to be abused, right? Because I mean, that was like the advertisement. It's like, oh, hey, it's going to be super hardcore and I'm going to exploit you. And everybody's like, oh, why don't I just leave then? But anyway, that's all beside the point. So when you're out working in tech or working at an engineering firm and designing robots for the mission to Mars or whatever, you're not going to be doing the stuff that you did in calculus. You're not going to be taking derivatives by hand. You're not going to be like, I'm going to use the product rule and the chain rule to find the derivative. Your boss will be like, oh, dude, we got millions of dollars of computers and you're doing shit by hand. What's wrong with you? Pack your desk, get out of here. Give me your badge. You know, that's just like not a thing. But the reason that those problems are important is because they help us start to figure out and give us some ideas to help us understand infinity. With the derivative, we want the slope of the tangent line. Slope needs 2 points. We only got 1 point because tangent. So we approximate with a secant line and make those 2 points infinitely close together. That's the derivative. That's how we're using infinity. We're making those 2 points infinitely close together. Delta y over delta x, we're trying to figure out what happens with delta y over delta x as delta y and delta x both go to 0. The derivative is pretty much going, what's 0 divided by 0? It's like, well, that's undefined. It's like, but not exactly 0, like getting close to 0. Very small. These are tricky ideas, right? And look, we've just dispensed with them with this derivative rule. We've got x squared here, and we're like, what's the derivative? 2x. That's how to find out what the slope of the tangent line is at any point. Amazing how that worked out. And then once again, there's the infinity of the area under the curve. I want to do length times width, but the stupid length is all continuously variable. Not just variable, continuously variable. So what do? We do the same thing that we always do. We approximate what we want, and then just see how to improve the approximation. We approximated the area as a bunch of rectangles. We took away the weirdo parts of our multiplication problem. The length is continuously variable. Not anymore. Now it's constant at a bunch of short bursts. Now we get to use multiplication, and then we just make the bursts infinitely short. And now shit gets really weird, right? Because before we were just adding up a bunch of areas of rectangles. We could see where to put the plus. Put the plus in between all the rectangle areas. But now we have to switch over to a continuum. Where do we put the pluses? It's amazing that we're like, oh, just find the antiderivative. It's amazing. And moreover, it's the inverse of the previous one. This is wild. This is crazy. What a great system we invented or discovered. The way that this works out. You know what I mean? It's the thinking that we get from that I care about moving forward. In 2 years, I don't really care if you can integrate by trigonometric substitution. I mean, you should be able to because it's going to be your favorite too. Spoiler alert, it's not going to be your favorite. I need like Morgan Freeman to just kind of like fill in those thoughts. It's going to be your favorite. It was not going to be their favorite. I can't do a Morgan Freeman voice. So I'm not trying to do a Morgan Freeman voice. So don't be offended, Mr. Freeman. I'm not trying to imitate you. But I do invite you to join my lectures. It'd be awesome. What's that? Oh yeah, he could do the what's the thing? I don't know if he does there's an app where you can pay celebrities to do stuff. And they record messages for you. I wonder how much it would cost to have an entire lecture, an entire calculus course, just like done by a celebrity. There you go. 1 million subscribers. I just need to get on TikTok, figure out how to make math, turn calculus into a bunch of 3-minute math lectures instead of these stupid 40-minute videos I put up on YouTube. On the plus side, having 40-minute videos on YouTube keeps your subscriber base very small. It is limited to people that are in my class or have been in my class and just forgot to subscribe. You know what I mean? So, but it really needs to be more like TikTok. Was that 3-minute videos? And that would be like the long, that's the longest you can make a TikTok, right? 3 minutes. So I would try to get it to a bunch of 1-minute videos if I could, like intro stuff, just like 1-minute video. This is what you need to think about. Anyway, because once I can get it down to that, I can just write a script and then ask a celebrity to read it, because that would be awesome. Oh yeah. Now I'd want to get the real person. Because what will happen? So this would be my ultimate goal. This is what's going to happen when I win the lottery in the middle of this, like in the middle of the year. So I always thought that I would retire right away, but if I win the lottery, instead of retiring right away, I'm going to take a semester off to make sure that any students that have been in my class before, I got rid of most of them, right? Most of them is not got rid of, like they graduate, they transfer, so that I come back and like no one's seen me before, because that's when I hire a celebrity to do the classes for me. So instead of like on the first day, I come walking in. On the first day, well, Morgan Freeman comes walking in, or my personal favorite, Dwayne "The Rock" Johnson comes walking in, and people are like, "Oh, is that The Rock?" And he's just gonna be like, "Oh, yeah, he is The Rock, but he will be portraying Professor Leach." And he'll be like, "Oh, good morning. I'm Professor Leach." I would leave it up to The Rock whether he wants to be called Professor Leach or just use the first name. Because I'll let y'all use my first name, but that's a little too casual for some professors. So maybe The Rock's like, as an actor, he'd be like, "Oh, no, I don't feel that." I'm like, "Oh, dude, I am literally Professor Leach. And I tell all my students to just call me Evan if they want to." He's like, "Oh, no, I'm not feeling that." So it's like, "Oh, hi, I'm Professor Leach," and it'd be like Dwayne "The Rock" Johnson, right? And he would just do the class. And he'd have like a little earpiece. I'd make it look like, it's like, "Oh, does Dwayne "The Rock" Johnson have a hearing problem?" Actually, they could be smaller enough. You wouldn't be able to see it, might be far away. And then if someone asks him a question, he just has to use his acting skills to stall. It's like, good question. And then I'm like, "Oh, no, I got you. This is what you want to say." And we just practice, and I tell him what to say. That would be expensive to do for an entire year. Yeah, that would cost a lot of money. But it would be awesome. Or I could just change up the person. So like the next week, like 1 week, it's The Rock, Professor Rock. The next week, Samuel L. Jackson. Anyway. What are we talking about? Oh, yes. The thinking that goes behind calculus. We have the thinking that goes behind calculus. We want to calculate a thing. There's some kind of continuity that's happening that prevents us from calculating the thing. So what do? We approximate. And then we just figure out how to make our approximation better. And then see, how do we make that approximation infinitely better? How do we do this? We do something more often. We just need to do it infinitely often. Take those 2 points and move them infinitely close together. Take that number of rectangles and make them infinitely thin. Now we're going to apply that. We can apply that. We have that thinking. We have calculus thinking. That is the thing that I want you to carry forward. That is why I care about this problem in Calc 1 before it gets ruined by the stupid arc length formula. It's okay if you know the arc length formula. I mean, it's like people worry about like spoilers in movies and stuff like that. Is anything really surprising in movies? Do you know what I mean? Like in The Walking Dead, it's like, oh, don't, if anybody gets killed, don't spoil it for me. And then they're like, oh, okay, I won't. It's like, oh, so someone does get killed. And I go, well, no, I mean, but yeah, it's like, well, so you're lying to me right now. So it's like a whole big thing, right? But the character's getting killed at random. So who cares if someone says, oh man, I can't believe they killed, I don't even know the characters on the show anymore. I can't believe they killed this character from that show. Like, oh, I haven't seen it yet. So we were gonna die anyway. You know what I mean? Anyway. So the reason that I asked you first, the distance from 0, 0 to 3, 9, shortest path along a line, before asking you the path, the distance along this curve, is that this is going to set us up. Remember what we do in calculus. We want to know a thing, but this continuously variable part is getting in the way. So we approximate. Here's our first approximation, kind of shitty approximation. Right? This is like all curvy. This is just like straight line. Easy to calculate though. This distance here, we're just going to use the distance formula. The other reason that I wanted to make sure that we had this, to make sure that we all knew the distance formula. The distance between these 2 points will be, let's see, 9 minus 0 squared and 3 minus 0 squared. So square root of 81 and 9, so square root of 90. Nine point what? 486. 487. I wrote it down earlier. 9.487. We know that if we do some kind of calculation, if we make some guess at how this is going to work, and our answer comes out less than 9.487, we have messed up. Can't be less than 9.487. There's not some extra dimension that this parabola is traveling through. I guess if I put a wormhole right here, like a little Mario warp, and it goes into warp here and then comes out there, then it's shorter. So we have a lower bound on what we're looking for.
So D is for what?
D for a distance formula. We have a lower bound on our distance for part B. Sometimes it's helpful to establish an upper bound on things. So just in that vein, I'm going to look at the L-shaped graph. I'm going to do extreme parabola, right? I'm just going to take my x squared, I'm just going to raise it to some ridiculous power, so make it more L-shaped. I'm going to go from 0, 0. I'm going to go horizontally to the point 3, 0. And then vertically, I missed. Make the point bigger. To the point 3, 9. So this distance along this rectangular path, this taxicab path, is 12. So that taxicab distance will be upper bound on the distance for part B. so-called taxicab distance because we're going from one point to another point, and we're pretending that we're on a taxi with streets and avenues. So even if I didn't just go one way and then one way, if I like went all zigzag, as long as I'm not backtracking, the distance is going to be 12. So if I went up one, right one, up one, right one, up one, right one, up the rest, I knew I'd lose track. That would still be a total of 12. Right? I was thinking about this yesterday. There needs to be a setting on GPS directions that you can just click on the button, and the button should just say, "Don't get cute." Because at one point, I was the place that I was driving to, I mostly knew how to get there, but I wanted to make sure. So I got off at 6th and I turned left on Harrison. So if you're familiar with San Francisco, I got off on 6th, but I took 280 up, got off on 6th. I like 280 better, even though the traffic there is just as shitty as 101. Got off at 6th, turned left on Harrison, and I was just going to take Harrison up to 9th so I could go over to Hayes, right? I don't know if you drive around the city, but that's what I normally do anyway. But I had the GPS on because I go, well, I need a reminder. So I turned left on Harrison, and the GPS is like, "Oh, get on the freeway." And I'm like, "Oh, motherfucker, I just got off the freeway. Why do I want to get back on the freeway?" You know what I mean? The other one too. I'm going, and I know that I'm going to be getting on the Bay Bridge. I'm not going to be taking 80. Is it 80? I'm going to take the Oakland Bay Bridge, right? I'm going to Oakland. I'm getting on that bridge. And it's like, "Oh, take 280. It's like, "Oh, no, because that's like all these surface streets that get you on the bridge. I'm just going to go directly through the traffic and get on the fucking bridge. Don't get cute by sending me down to all these surface streets. I don't care if it calculates that it's going to be a couple of minutes faster, because that's the theoretical time that it's going to take, not the actual time. Do you know what I mean? And I would rather not have to make 1,000 turns when I could just be on the freeway the whole way. You know what I mean? Even if there is traffic. Anyway, so taxicab distance. As long as we just, if we go from point A to point B, horizontal and vertical only, low res, then that's what we'll get. So we've got a lower bound and an upper bound. If we get more than 12, we messed up. If we get less than 9.487, we messed up. We've got to think about how we're going to approximate this length with the tools that we have and our calculus thinking. What could we do? Suggestion? Yeah.
You find that area divide that area relative to the entire triangle and multiply the difference between the upper bound and the lower bound.
Wow, that's kind of awesome. I kind of like that. You should definitely try that. Did you do that yet? Okay, well, you have a direction to go. I kind of like that. We got to see if it's going to work, but I like that one. That one's pretty dope. If that works out, we're going to have to think about why that works out. Excellent. I like that. That's not the one that I had in mind, but I like that. We should try it. Everything we should try. This is science. We're doing science right now, right? Yeah, keep trying. Try something. If something doesn't work, try something else. How can we now remember? I started with this one, not just to get a lower bound, but this is how we calculate the distance between 2 points. So I want you to think back to the beginning of the class and the two big questions that we have about calculus and how we use those to get at the big idea of calculus, the story of calculus, which is infinity, the infinitely small, the discrete, the continuous, ultimately just infinity. We wanted the slope of the tangent line, and we had the slope formula and said, this is how we calculate the slope of a line. And then the problem arose, well, we need 2 points for that. We only have one. So we had to modify what we already knew to get at the problem that we didn't know. Area is equal to length times width, but the length is continuously variable. How do we modify length times width to take what we already know and apply it to what we're trying to know? This is how we calculate the distance between 2 points. How can we modify this? This is how we calculate the distance between 2 points and modify what we already know and apply that knowledge to what we're trying to find out. How do we take that straight line distance and use it to approximate the curvy distance? What can we do? Make an infinitely small line. That seems like that's like going right to infinity. We haven't talked about how we're going to do an approximation in the middle. Let's take it back one step. Remember, there's modifying our technique to fit to go after the thing that we want, and then we apply infinity. So what would that first step be? What would it look like? What's the low resolution version of your suggestion? Any ideas? What did we do to find area? We took that smooth line and we broke it up into a bunch of flat lines, a bunch of blocks. We took our resolution and we just turned it down. So instead of doing a bunch of smooth lines, we just like a bunch of flat lines. We just stacked up a bunch of boxes. Low resolution version of the area. Pixelate the area. And then we just use smaller pixels. We got the distance between 2 points. We have a method for the distance between 2 points. How do we take what we know and use it to approximate what we're trying to find out? Sure. 10.325, we'll call it 5. That is a little bit high. So that's a little bit higher than our arc length. Raises questions though, raises questions. Why was it supposed to work? Why didn't it work? Right? That's like the big idea behind that. That's the thing that I didn't really understand very much about when I was in chemistry. And that, so full disclosure, I think the statute of limitations has run out. In chemistry, since we were supposed to get less than 5% error, I just picked a number that was less than 5% and I made the measurements afterwards. Right. So I just went, I'm like, oh, well, I just did like Mythbusters if it was just a math show instead of like a fun engineering show. Right. So you want less than 5%. So 4.87% error would be okay. All right. So 4.87% error means this was going to be less than this by what I expected. So I'd measure at the beginning, and instead of doing the experiment and making a mess and then having to clean up, I would just pretend that stuff happened. And it worked out to 4.87% error. That kept me under the radar. Successful completion of chemistry lab. Unfortunately, then it took me much longer to learn that getting stuff wrong is very valuable. At the time, I just thought it was bad to get stuff wrong because school ruined me, right? And it's probably done the same thing to you. And that's what I'm trying to get rid of. Got to fight that. It's great to be wrong because then you get to think about what happened, right? So 10.325, I think, is not the correct arc length, unless I'm misremembering the arc length. So the question is, why was your method supposed to work? Why didn't it work? If in fact it didn't work. So what we want to do is how do we take what we know which is the distance formula, and apply it to the problem at hand. Our arc length. How do we take what we know, which is the distance formula? That's how we find the distance between 2 points. But it's limited because this is a straight line distance between those 2 points. Now I want this curvy distance between 2 points. How do we take what we know and apply it to the problem? How can we take that approximation method? So this is some kind of approximation method. So the question is, what's our approximation method? Once we have an approximation method, how do we apply calculus thinking? How do we go to infinity? Once we have our method, how do we do the calculus thing? Once we have a plan, what does it look like in the algebra? You have an idea? Nine point 9.676. I actually don't remember. How did you get the 9.676?
Okay, so basically, I took the distance equation formula, whatever. And I do it for 1, 0, 2, 1, 3.
So from 0 to 1, from zero to 1, and then
1, 2,
from 1 to 2, then from 2 to 3.
it's just, and
So, but then you just did the distance formula 3 times. So you just made a line from 0, 0 to 1, where would it be? 1, 1. And then a line when x is equal to 2, what are we going to have? A little steeper. So this is how we can take what we already know. We know we can find the straight line distance between 2 points. Let's just take this straight line and start bending it into the shape of a parabola. So great suggestion. So look at this. Here's the point 0, 0. Here's the point when x is 1. Let's see, it's along the y equals x squared. So 1, 1, and then 2, 4, and then 3, 9. So instead of just making one distance from 0, 0 to 3, 9, we've now 3 distances. They're all straight lines. So we could just use our distance formula, and then we add up those numbers. How can we improve this approximation? Squish them. Squish them together. Right now, the distance between the points is 1. So now, next, make the distance between the points a half, then a quarter, then stop doing by 2s, a 10th, a 100th. Then see what happens when the points become infinitely close together. Any questions? That's the calculus thinking. This would lead to an integral. Right now, we're not well versed in integrals, but that's okay. This would lead to an integral, and it's an integral that we wouldn't know how to calculate, except we do have some friends that can calculate it. Not my dog. My dog is terrible at math. My dog is terrible at calculus. He's pretty good at math. But so we would need some kind of machine to help us calculate until we learn how to calculate by hand. Then once we learn how to calculate by hand, we can say, wow, I hope I never have to do that again. I've got a machine to do this for me. But that's the calculus way. What do we know how to do that's related to the problem? How can we make that how can we use that to model the problem that we're after? And then how could we make that model better by introducing infinity, by barfing some infinity on it? One last note, here's the truth about dogs. Dogs can count, but they don't do fractions. So like some people like make fun of like if you take a cookie and break it in half and then give the dog doesn't know it got half a cookie. If you take one cookie, break it in half, the dog says, I just got 2 cookies. Heck yes. There are some times when I wish you could think like a dog, you know. They're much more optimistic, generally. If the dog was raised properly, they're much more optimistic. But I gotta tell you, I could take the same piece of chicken and I could give that to my dog once. I paid him once. But if I break it up into 4 pieces, I might go, good job, buddy. And I pay him 4 times, like, oh shit, I got paid 4 times for that one. I'm definitely doing that some more. Question? With your method? With the area thing? Yeah, a little bit. That's okay. Overthinking is great. But this is a great idea. I like this. Now, we know what we're doing. We know what has to happen. These need to get closer together. Well, shit, now it's time for algebra. Algebra has entered the chat, and everybody's like, oh, let's find a reason to leave. All right, that's going to do it for today. I like the area thing, though. If you could make a relationship between area and perimeter, right? Because you know this one and you know that one. If you could find the length of that one, that's what you're looking for. Is there some kind of relationship there? That's one of the things that I was thinking of with the area thing. Everybody have a nice long weekend. I'll see y'all on Monday.